continue talking about forward kinematics and DH parameters, which are the four parameters that are used to determine the transformation matrix from two joints, or basically from two coordinate systems in a robot arm. And we have seen what I'm just basically seeing now in the slide, the DH parameter, which is called DH1 parameter. Now, what we will see next is something called DH2, which is the most common. Now, what you will see that the difference is, first, it's the I and I plus 1 in the DH parameter or DH1 parameter, which will be basically later is basically the I minus 1 I. And the difference is that DH1 represents the coordinates of the next joint, or for example of the joint I plus 1 with respect to the joint I. So it's doing backward transformation. Okay, that's very important to consider. When it comes to DH1, it is backward transformation, which means if I have a coordinate system x1, z1, y1, which transformation I have to do to transform this back to the for example, x0, y0, z0. Now DH2 is the other way around. Is basically I start with a coordinate, or I start, let's say, with the transformation or with the coordinate system of the frame. Then I go forward. So which transformation I want to do or want to have my first transformation to the first joint, then to the next joint. So this is basically, if I look now at the next slide, which is in session 7, and this is how actually we started. This is basically DH1, and this is basically the representation of DH1, or actually how we derive the DH1 matrix. Now, as I said, the idea there is that we make backward transformation. And it is between, for example, this joint and, which, for example, I plus 1. How can I come back to I? Now, I want you to consider the order that we see here. So we have, as I said, two transformations and two rotations. Two transformations around, for example, two translation and two rotations. Two translations along one is along the z-axis and one is along the x-axis, and two rotations, one around the z-axis and one around the x-axis. Now, if I just look here, this is a chain of transformations, and when you see chains of transformation, that means we would multiply the chains of transformation with, let's say, coordinate system on the right side, and we want to transform it back to the next coordinate system, or not back, could be forward, but basically we have a coordinate system here, or let's say coordinate, let's say a point in the 3D dimension, and once we multiply this point coordinates with this chain of transformation, we are taking now the new coordinates of this point with respect to the transformed coordinate system. Now this chain has an order, and this order is very important to consider. And whenever we have chain like this, basically the first one here is the one that would be applied first. So it's not this one is the first one. This one is the first transformation, then followed by this transformation, then this one, this one, because this one, the one that will be multiplied by joint, then this, then this, then this. Now, if I look here, what I see that when it comes to DH parameter or DH1, that first I have rotation around X, then translation along X, then rotation around Zn minus 1, which is the previous joint. And here translation along D, or along, sorry, Zn minus 1, which again, the previous joint. So if I look back at this example we had here, as I said, DH1 is backward. That means I have, for example, x1, y1, z1, and I want to transform it back to x0, y0, z0. Now here it suggests that first I need to have rotation around x, because as I said I would have, so this basically would be multiplied by x1, z1, y1. So this is basically the coordinate system that will be multiplied with, which will transform it to the x0, y0, z0. Now the first thing I want to do according to this formula is the first is rotation around x. And we can see that the first thing, yes, I want to do here, if I want to rotate around the x1 axis, so basically the xn here, because so x1 axis. Just if you are confused, here it's n minus 1, and this is I plus 1. It doesn't really matter. What it matters is that basically it's the transformation from the next to the previous. So in this case from I plus 1 to I, and this basically from n to n minus 1. Now here we have, as I said, we have basically the first thing to do is rotation around the x1 with here alpha. Then we have translation along the x1 axis with the distance Rn here. It's basically as a different reference, but in this case is the distance along the x-axis is always, not always, but in our case here is a. Now if we read here the distance along the x-axis, here it's I plus 1 and there is actually n. And here it is basically from z1 or from zi to zi plus 1, or in this case from zn minus 1 to zn, with a sign taken from xi plus 1 in this case, or xn. Now if we look here, I remember we talked about this in the last lecture, in this case there's no distance between z1 and z0, because especially with respect to x1, z1 and z0, they are on the same plane. So even if I rotate, they are still in the same plane. So they have no offset, they have no distance between them. So that's why the translation there's no translation. So it basically becomes not translation. So it will be equal to 1. So it will not change anything. So basically you can consider that not relevant here. It's not 0. So that doesn't mean that we are multiplying with 0. No, we are multiplying with basically this transformation matrix, where here R1 is basically is equal to 0, but that will not change, will not do any translation. Now the next is rotation around Zn minus 1. We do need to have the rotation around Zn minus 1, because now if I do basically the first rotation around x, actually we don't need to do any rotation here. So if I have that, then it would be, if there is rotation, that would be considered by theta n, which is a variable. But in this default case, there is actually no rotation, because if I rotate around the x1, then I have z1 and z2, they are aligned, and I have actually y1 and y0 are aligned. If there is theta, as I said, then there will be basically the angle that we have there, which is basically theta 2. But there is no theta in this case, the standard or default position like this. The next would be translation around or along Zn minus 1, which is basically the translation along this, okay, Z0. Now what we have here is that correct, because first I did rotation around the x1, then translation along z0, and in this case if I do this too, I can bring back this transformation to or the x1 z1 y1 to x0 y0 z0. Okay, so this is basically the first rotation, which is a 90-degree, or actually in this case would be, we are talking about counterclockwise as a positive, so it would be basically minus 90, because I'm going in the clockwise basically direction. Then I have no translation along x, and more specifically along xn. I have no rotation around z0, which just means theta 1 here is standard. But if there is rotation, then we can apply it. This is not an issue because it depends on what is the value of theta 1, okay? Because theta 1 is our variable, remember, which is coming from the motor or the actuator. So if there is here, yes, it's basically we can consider it. If it is as here, which is basically 0, then we don't consider it. But in general, when you have this multiplication, theta should be always a variable, so you need to keep it as a theta, so as a placeholder, so you don't need not to put any value there. And then we have the last translation there, which is along the z1, z0 in this case, or zn minus 1 here, which bring back to the reference. Okay, so this is basically the DH1 parameters. Now DH2 is, as we'll see here, it's quite similar, but the different direction. It's basically taking the from I minus 1 to I. Okay, so it's just the forward direction. And if I look here, it's basically kind of reversed order, because what we see here, we have first translation basically along the z, then rotation around z, then basically translation along x, then rotation around x, which is basically, as I said, the reverse of that, because we are just doing not backwards but forwards, which is basically from I minus 1 to I, instead of in that case it was from I plus 1 to I. Okay, now because of this we would see different transformation, of course, because we have different order of multiplication. And this is basically this is the first DH1 parameter, and this is DH2. And here we have an example of a robot arm. Now basically this robot arm exists in our lab in transportation informatics. So this is called, actually I forgot the name, but it has two versions. One is 4 degrees of freedom and one is 5 degrees of freedom. The one in the lab has 4 degrees of freedom. The difference is that this last joint here, which can have this kind of rotation, this is the 5 degrees of freedom. In our lab, the one that doesn't have the rotation, so it has 4 degrees of freedom, which means it has 4 joints actually and 4 actuators. And so basically, if I look at the coordinates diagram, what we want to do now is to estimate basically the DH transformations. I want to do the DH2 transformation, which means that I want to go forward, which means like what is the coordinates z5 and or z6 actually, which is the last point, which is the end effector, with respect to the base transformation. So let's do it together. So first we have when it comes to DH parameters, and we'll see another example later. It would be easier, of course, if it's not online, but on premise or physical media, because then we can do it on board. But basically, what you need to do is you need to put like the order of joint like we have here. So we start with 0, 1. So basically we have to define a matrix or a table. And this basically in the exam you have to create a similar table. So the first table is doing the transformation from 0 to 1. So from joint 0, which is a frame, to 1, then from 1 to 2, then from 2 to 3. Then here we have from 3 to 4 in case of 4 degrees of freedom arm, but in this one we have again the last one, which is from 4 to 5, and we have the last, which is for the reference point, which is from 5 to 6. So 5 is the fifth joint, and 6 is the end effector reference point, which is basically, as I explained in the previous session, it's more like translated version of it. Now here we have the 4 parameters. This could be S or D in some cases. This could be A or R. So it's basically this just a different naming, I would say, orientation. Now what I want to do is look first at the first joint, which is from 0 to 1. So if I look back here, 0 to 1. So this is basically x0, y0, z0. Now this is z1, y1, x1. Okay. Now, if I look there, there is only, first of all, translation. There is translation, and there probably rotation or the first control point or control variable, which is theta 0, let's call it there, because this is the first joint that we have, which is this one, and this basically has rotation around the z. As I said, always the base or the shoulder is called in Robotics. It has this kind, basically the shoulder base, so it has basically kind of this rotation, okay, around z. Now I have from, this is basically, so this basically would be my first theta, but let's look at the parameters of dh2. A is the distance along z, along x0 in our case for the first joint, from z0 to z1. So if I look here, we have a distance again along x from z0 to z1. Now z0 and z1 are on the same plane. Actually here they are on the same line even. So there is no distance between them. So what I can do now, I can go to my matrix and put A as a 0, because there is no translation there at all, and this is fixed. This is basically is not a variable. The next thing here we would have is that now, which is the next parameter, is alpha, which is the angle from positive z0 to positive z1, taking basically counterclockwise as seen from positive along x0. So we have an angle between z0 and z1 if basically with respect to x here 0. There is no angle, right, because z0 and z1 will be always aligned. So this is why, because there is no joint there that can make this movement, so it's basically it's fixed. This is why basically alpha there is here in this case is 0. Now for the next joint we would have or the next parameter, we have theta. And now theta, we do have theta because theta is the one that rotates around z0 in this case, right? So basically it is the rotation z1, sorry, is the rotation around z1, and which creates an angle between x0 and x1. So basically this x0 and this x1, and rotation around z1 or z0, they are same basically. And this basically the rotation of this joint, yeah. So basically that moving the robot arm in these directions. And this is my first theta, so basically the first control parameter that would basically be used, sorry, not this one, be used by the motor. So this basically would be here, or by the first actuator would be theta 1. The last one, last parameter is, actually we see it here, it is called d1, which is a distance along z1 from x0 to x1. Okay, so this is x0 and this x1, and the distance along z1 or z0 same, and this basically the d1 that we see it here. So this basically is my d1, or as I said, we can call it s1 and so on, basically, or d1 in this case. And this is given, so this is basically this is not a variable, should be given, okay, because this robot arm doesn't have translation between x0 and x1, so there's no, let's say, prism joint here. Now this we finished from transformation from 0 to 1. Now the next one would be from 1 to 2, and this basically, you can see that we have z1 there, x1, y1, and we have z2, x2, y2. So they are on the same point, but there is basically the rotation that is applied by this joint, and it's basically the rotation around z2 as we see it here, because as I said, z2 should be always the axis of rotation in robot and manipulators. So the z-axis. Now I need the four parameters. The first parameter again is a, which is the distance along x, for example in this case along x1 from z1 to z2. So this is basically x1 from z1 to z2. z1 and z2 are the same plane with respect to x1. That means there is no translation there. So again, this is actually 0. Next is the alpha, which is the angle basically from positive z minus 1 to z I minus 1 to zi, which is from z1 to z2 in this case. There is an angle between z1 and z2 as we see it. This is 90 degree, right? So this is z1 and z2. If I'm looking from x2 counterclockwise, positive, which is basically 90 degree. Now here we have theta 2. I can directly put it because it's my control variable. Is there now distance between the two x-axis? No, you can see they are on the same line. That means basically it's equal to 0. Now you need to continue doing the same for the rest of the joints in the same way. I will do the next one, and then the last two I will leave it to you basically just to practice. So now I want to do from x1 now from x2 z2 y2 to now x3 y3 and z3. Now z3 is if you look here, it is basically this one, which is the axis of that joint. It's hard here to look at it, but basically you can consider it as something like this. Now, which means if you look here, it's easier to look basically because this is z2 and z3 is there. Just remember when we have this case, so when I have actually a link which has two rotational joints, they are the two z's basically are parallel to each other. Just always consider this, and also would be the same case for that. So they are parallel to each other, which means now I can use this information. So I have first the distance from now x2 or along x2 from z2 to z3, z2 to z3, right? So z2 is this one and z3 is this one, and is there a distance with respect to x3? No. So it's basically you need to consider that there is no distance there. If we in this case it's hard to see because there is an angle somehow, but basically z2 and z3 they are on the same plane, and whenever they are on the same plane there is no distance between them. Or let me just check. No, actually that's wrong. So it's basically here it is the distance is alpha 3, okay? Because if I put this on default, okay, which means if it's a good way to look at it. If I basically put theta here 2 at 0, So this would, we have a line there, and put this set at 0, then we would have also a line. So x3 would be basically in this direction, okay? And then the angle basically between the distance between z1 or z2 to z3 along x3 would be alpha 3. So if I let's give you here an example, what I have done there is, this is the first link and this is, let's say, the second link. I want to just, what I said is, let's to put everything basically on the default. And here it's telling me that basically x3 is here, is basically, or there, it's along the axis there. So when I do that, rotation would be this direction, and I would have then z2, and this is z2z basically, but there I have x instead of y, okay, because x is in the upper direction and the distance between them is alpha. So what I need to do there is put alpha 3. Now, is there any angle between the two? So if we look back here, the next one is alpha, which is the angle between the two z-axis, so z2 and z3. Now there is no, this is basically, there's no angle because they are parallel. So basically this one, I said they are parallel, so this would be 0. This now would be theta 3. Is there a distance between the two x-axis? No, they are on the same line, so this basically would be 0. Okay, so this basically, now you can continue with the rest. If you have find difficulties to get them, as I said, try to put it in the standard where thetas are zeros, just to see how they look like. This is another example where we have basically x along the link. So it's always like this. You need to consider as well with robot manipulators rotation. So the control parameter is always around z-axis, which is basically the degree of freedom that it has, and it always said that the x is along the link itself. Okay, this basically, it's important to consider as well to solve the problem. So I will just conclude this session. Next session I will give another example of forward kinematics, and then we'll talk about inverse kinematics. Thank you.